So by rearranging the equilibrium expression for the dissociation of a weak acid, we can find that the concentration of H plus and therefore the pH really depends on this ratio of the weak acid to its conjugate base. So in the previous video, we did an example with buffers where we started with 0.5 moles of 0.5 molarity of acetic acid and acetate ion. So this ratio was 0.5 over 0.5, or just 1. And then we added hydroxide ion to that buffer, and after the hydroxide reacted with acetic acid, we had 0.49 molarity of acetic acid and 0.51 molarity of acetate ion. But this ratio, which is now 0.49 over 0.51, is basically the same. It did not change very much after we added the hydroxide ion. So we do not want this ratio to have a significant change. If this ratio of the concentration of the weak acid to its conjugate base does not change very much, then the pH will also not change very much. So we can modify this expression to get a convenient equation for finding the pH of a buffer solution. So the first thing we do is take the negative log of both sides. And remember, if you have two things multiplied by each other inside a log expression, you can split it up with addition. And since it's negative log here, it would be subtraction. So we split up the log of this. And then the negative log of the concentration of H plus is just the pH. We know that. And the negative log of the Ka of the weak acid is called the pKa. So P basically just means negative log of something. And then, if you remember, we can take the coefficient of a logarithm, here it's -1, and bring it up to an exponent, which would flip this expression inside. So this turns into a plus sign, and then this ratio is flipped so that it's the concentration of the base over the concentration of the acid. So this is called the Henderson-Hasselbalch Equation. So the pH of a solution will be the pKa of the whatever the acid is, plus the log of the concentration of the base over the concentration of the acid. So if a buffer consists of a weak acid and its conjugate base, this will be the concentration of the conjugate base over the concentration of the weak acid. And then the pKa will be the negative log of the Ka of the weak acid. Whereas if a buffer is a weak base and its conjugate acid, this will be the concentration of the weak base over the concentration of the conjugate acid. And this will be the negative log of the Ka of the conjugate acid. So let's say we have a buffer solution with 0.25 molarity of ammonia and 0.4 molar of ammonium chloride. So here a conjugate pair is the weak base ammonia and its conjugate acid ammonium. So we could find the pH by doing an ice problem, but that takes too long, so we can just use the Henderson-Hasselbalch equation. And you'll get the same answer because they're basically the same thing. We derived the Henderson-Hasselbalch equation from the equilibrium expression, which we use when doing an ice problem. So the Ka of the acid here, ammonium, is 5.6 times 10 to the -10th. So we take the negative log of that, and then the log of the ratio of the concentration of the base, NH3, to the concentration of the acid, NH4+. So This is 0.25 over 0.4. And then plugging that in, we get the pH is 9.05. So this buffer solution is slightly basic, which we'd expect since the main thing here is ammonia. Ammonia is a stronger base than ammonium is an acid. So we can find the pH change if we add 1.1 mole of hydrochloric acid to 1 liter of this buffer solution. So when we add the hydrochloric acid, it will dissociate into H plus and Cl minus. And then the extra H plus from the hydrochloric acid will react to completion with the base, ammonia, because the ammonia is attracted to protons since it's a base. And this reaction will go to completion, hence the single arrow instead of the double arrow. So remember, this is just a stoichiometry problem, so we use moles instead of molarity. So you have to convert between the two. And here it's 1 liter, so the moles and molarity will be the same. So the reactants will lose 0.1 moles, since H plus is the limiting reactant, and then ammonium will gain 0.1 mole. So these are our final amounts. Now at this point, we'd have to convert between moles and molarity again. And then we can calculate the pH of the new solution using the Henderson-Hasselbalch equation. So the new ratio of base to acid is 0.15 over 0.5 molarity. And so the new pH is 8.73, which again is not a large change from the original pH, even though we added a very strong acid. So the last thing we're going to look at is buffering capacity, which is just how much hydroxide or H plus a buffer can absorb without having a large change in pH. So we already know that in order for a buffer to work, the concentrations or amounts of the acid and its conjugate need to be much larger than the amount of whatever we're adding, the hydroxide or the H plus. So the more weak acid and conjugate base we have, the larger the buffering capacity will be. And looking at this ratio of the concentration of the conjugate base to weak acid, the optimal buffering occurs when this ratio is 1. In other words, the concentration of weak acid and its conjugate base is the same. Because if they're the same, then this ratio will change the least when we add an OH minus or H plus. And so if these concentrations are equal, putting that in the Henderson-Hasselbalch equation, this ratio of 1, well, the log of 1 is just 0, so the pH will equal the pKa if these concentrations are the same. And so when we choose which acid and which base to use for a buffer, we will need the pKa of the weak acid to be close to the pH that we want the buffer to be at. Since if we have this optimal ratio, the pH will equal the pKa of the weak acid.